Okay, thank you for the invitation to present the TMS. It is a great honor to be part of this session. I have fond memories just of last year being in San Diego. It was the last meeting before we all got grounded. So it's great to be able to come back in some form and participate. I'm going to tell you a little bit of a story today about some of the work we've been doing on cathode design across scales. And I'll start out by just saying upfront that the moral of the story is really the urgent need to bridge scales, starting from understanding atomistic phenomena all the way to mesoscale phenomena and then to electrode level phenomena. So I'm going to try to present V2O5 as a model system where we've tried to understand comprehensively mechanisms of ion diffusion and to understand how by tweaking atomistic parameters, by single particle parameters and mesoscale parameters, we can control both the accessible sites, the specific diffusion pathways, and the kinetics of diffusion in the material. And so I'm going to thank the group that has done all this work. A lot of this work started from some very fundamental electronic structure studies that Jesus Velazquez in my group carried out, and he's now at UC Davis. Greg Horrocks looked at some single particle phenomena. Luis de Jesus did a lot of the work on scanning transmission X-ray imaging. And today, I'm going to be mostly spending time talking about the work of Luis de Jesus, David Santos, who's worked on X-ray imaging of lithiation heterogeneities, Justin Andrews, who's done a lot of work on stabilization of metastable V2O5 polymorphs, and then Joseph Handy, who's worked on different aspects of single crystal electrochemistry. And this is something we're pretty excited about, the ability to look at diffusion pathways at the atomic level through single crystal electrochemistry. I'm not going to get a chance to delve too much on the anode side of things, where Rachel Davidson's done a lot of work along with Parker Schofield. And a lot of collaborations here. Especially want to acknowledge the group of Baishang Xu at TU Darmstadt, who has worked with us on many different aspects of mesoscale modeling, multiscale modeling, as well as Partha Mukherjee at Purdue, David Prendergast at LBNL on some of the X-ray simulations, and colleagues at the Canadian Light Source who have enabled many of the experiments that I'm going to be speaking about today. So just a very quick overview that perhaps this audience doesn't need, but we're in the midst of an unprecedented change in paradigm as far as energy is concerned. And a big part of this puzzle is going to be energy storage, right? So what are we going to do there? Are we going to store energy, especially as we move towards a greener energy future, but also sometimes a more uncertain energy future where we have multiple different players in the mix, including wind and solar energy that can be intermittent in nature. So we've got a big task ahead of us, both for large area grid level storage as well as for applications like electromobility. So these are the ones that are driving much of the excitement in energy storage. The global demand for batteries at this moment is driven by electromobility, but increasingly grid storage, load leveling applications are coming into play. And it's really important that I think it's becoming pretty clear that there's going to be a whole range of solutions that are going to be required depending on the power density and the energy density needs, and lots of other constraints such as safety, portability, and criticality of the materials involved. So there's a whole plethora of different options to keep in mind. But I think this just makes it a really exciting time to be engaged in energy storage. And perhaps a sobering thought comes from this idea here that, even despite this large push on energy storage technologies, we've only had about a 4-fold improvement in energy density over the last 160 years. So we need some new tricks. We need to also be able to start seeing what are the bottlenecks that are preventing us from accessing some of the theoretical capacities of materials. And I would argue that this is really a multi-scale challenge, and it requires understanding of the entire range of phenomena, starting from atomistic design to electrode level parameters. So as a very elementary sort of way of thinking about this, here's a wish list for an intercalation electrode. So we've got to get both the thermodynamics right and the kinetics right for any of this to work, right? So on the one hand, we need a large free energy difference between intercalated and deintercalated phases. So especially if you're talking about a intercalation battery, or really between a discharge and a charged phase, but not so large that is thermodynamically impossible for us to go backwards, right? So this has to be reversible. We need a relatively small lattice change upon insertion, and this is becoming especially something that people are getting very concerned about as we start understanding the role of mechanics, and the coupling of mechanics with electrochemistry is of paramount importance. Then we need an abundance of interstitial sites as well as accessible redox centers for this chemistry to be possible. Okay, and then in terms of kinetics, okay, well, the ions are going to have to diffuse within oftentimes crystalline lattices, so side-to-side diffusion barriers have to be low. And it's not enough to just have bulk diffusion. We also have to have the solvation, desolvation processes that happen at interfaces have to be quite facile. And then intercalation reactions have to be strongly favored over all sorts of other reactions that can also happen, such as conversion reactions or other surface reactions. Okay, so starting here, again, the idea of designing across scales, of course, the atomistic parameters matter, but also single particle phenomena, mesoscale phenomena, all the way up into electrodes and full cells. So that, and a lot of, I'll talk about how some of the problems that we see at this end stem from issues that get initiated at the atomistic level, and how resolving some of the phase heterogeneities and chemomechanics coupling can help then address issues such as cyclability and also longevity in general. Okay, so we're going to pick V2O5 as our model cathode, and by this I mean vanadium pentoxide, V2O5 discomposition, and this is the thermodynamically stable polymorph of V2O5, and as you can see, this is a really attractive electrode material. So Stan Whittingham's early work looked at this several decades ago at the advent of lithium-ion batteries. There's a lot of work going on. And the reason, you can see why it's so attractive. It's got these this sort of layered framework, lots of open sites in between for lithium ions to be accommodated. And then you've got this vanadium 5+, which can be readily reduced to 4+ and 3+. And so there's clearly a lot of room to store lithium ions through redox chemistry. Okay, and you can see this here where you've got some of the sites for lithium ion storage delineated here. But this is, while this is the thermodynamically stable polymorph, what I'm going to spend a lot of time in my talk talking about is how do you re-engineer this phase? How do you change atomistic configurations to stabilize metastable polymorphs that oftentimes can do a lot better in terms of mitigating some of the deficiencies of this particular framework, okay? And I'll speak to some of those deficiencies in a second. So lots of great properties that straight out the bat we get out of V2O5. It's got a pretty high theoretical capacity of about 440 milliamp hour per gram. You can access multiple redox states, and you can do intercalation chemistry very readily in these galleries between the layers of V2O5. The undesirable issues that people quickly found out, and this shows the sequence of transformations that happen starting from V2O5 to this alpha slightly distorted structure into this more puckered framework, still layered epsilon V2O5. And then you get some translations to happen. The ions, the layers slide along each other. You get this delta phase, and then ultimately going to a gamma phase. And then at still higher lithium concentrations, you stabilize this cubic omega structure. So some of these transformations, especially beyond gamma, are irreversible in the bulk, and this is a real challenge. The diffusion kinetics can slow down, especially for these highly lithiated structures, and the electrical conductivity is not great because of the large band gap in this material. So these are all issues that we need to resolve, and I think our ability to both control atomistic structure through design of different polymorphs, as well as to understand how to control particle morphologies in this system, provide a real good handle for understanding some of these multi-scale interactions that are at play here. So trying to understand what are the origins of some of the challenges with the system. So in alpha V2O5, like you see in this animation, there is the lithium ions have to go from an 8-coordinated site through this trigonal planar 3-coordinated site and then into another 8-coordinated site. Okay, and this is a fairly large amount of bond breaking and bond making that must happen, and then the ion has to squeeze through a relatively narrow transition state, okay, to get to its adjacent side. And for lithium, this is not completely impossible. You can see for other ions like magnesium, this becomes really, really challenging. Almost an EV worth of energy is how much is required to squeeze the magnesium across these barriers. This is the structural parameter. In terms of the electronic parameters, so the square pyramidal coordination of vanadium is not ideal, because it essentially, just from crystal field splitting, it gives you the dxy state as the lowest lying state at the top of the conduction band, and this narrow split off conduction band during early stages of lithiation serves to localize electrons. And so the electrons are not very mobile through this lattice, and this is also a challenge in the system. And then something we've spent a lot of time looking at is the coupling of the localized electron in this dxy state with the lattice, which then induces this distortion, as you can see here in the simulation. And there's plenty of experimental evidence for the formation of this local lattice distortion, which is essentially a small polaron. Okay, and then the small polaron can interact with the lithium ion and give you a self-trapped polaron, and the self-trapped polaron can find it quite difficult to diffuse through this V2O5 crystalline lattice. Okay, and again, where this is coming from is this dxy being a split off conduction band because of the square pyramidal nature of coordination of vanadium and V2O5, which then gives this very narrow band. Okay, and so as you get lithiated, because of the unfavorability of the square pyramidal oxidation state, the lithium structure, the V2O5 structure actually tends to start becoming more octahedral, and the whole series of phase transformations. This is a phase diagram that Justin Andrews has collected from really vast amounts of literature. So really data dense phase diagrams showing the changes in volume and changes in the ABC and lattice parameters. And there's lots to see here, but in the interest of time, I just want to draw your attention to these extended phase stability regimes, phase coexistence regimes, where you will have windows of alpha plus epsilon or epsilon plus delta, and so on and so forth. And this phase coexistence has lots of implications, both in terms of the kinetics of the system in creating these phase boundaries between differently lithiated phases that serve to block lithium ion diffusion or to create impediments to lithium ion diffusion, as well as for generating mechanical stresses as a result of the lattice mismatch at these interfaces. And so once you get to gamma, then this transformation is generally irreversible, and that then also creates a whole other set of problems. So, okay, if I were to look at the electrochemistry here, you can see the structure change as a function of the lithium ion concentration, okay, and the layers pucker and get more and more distorted and start pulling apart, okay. And in terms of the electrochemistry, you see distinctive plateaus corresponding to alpha to epsilon, epsilon to delta, delta to gamma, and so on and so forth, okay. And again, these summarize the challenges between ionic diffusion, electronic diffusion, and really, perhaps most importantly, the coupling of these two phenomena between as a result of small polaron formation. And as distinctive evidence for small polaron formation, we've studied this a fair bit. We saw some signatures of small polaron formation that I'm going to show you in a few seconds in X-ray absorption spectra. We saw the Pauli blocking of DXY states, but this right here is some beautiful RIX data where we can see the DXY derived polaronic states increase in intensity, and the X-ray absorption spectra show that the unoccupied DXY states are decreased in intensity. So some really smoking guns for this DXY polaron is being formed in B205. And I think it's particularly compelling also the value of such analysis is to be able to really dive down into detail and to be able to identify the specific orbitals that are involved in giving rise to these polaronic bottlenecks, which are really of paramount importance here. So we spent a lot of time using X-ray microscopy and X-ray imaging and picography to look at some of these heterogeneities in these systems using focused X-ray beams. We can see here some of these polaronic signatures that I was talking about. You can see this in a little bit more detail. So this DXY peak, which is the split off conduction band here, is decreased in intensity as you lithiate more and more, okay? And we've got some beautiful high resolution spectra. Again, the work of Justin Andrews and David Santos, really looking at these spectra. We can see that the DXY peak weakens, and so we've got some really great standards that we can assign any spectral data sets to, right? And so you can see here the DXY bands diminished. Another signature of this, the oxygen K edge, is the change in relative intensities of the T2G and EG star states, and this is happening again because of structural distortions modifying the vanadium oxygen hybridization, but really from a lot of DFT modeling done in collaboration with the Prendergast group, it's because of the loss of degeneracy of spin up and spin down states once you go from a D0 to a D1 system, and this causes. So we've got two ways to really identify very precisely the D electron density as once lithiations have started to happen. One using the DXY feature of the vanadium L3 edge, and then the relative intensities of the T2G and EG features at the oxygen K edge. And what we do in a scanning transmission X-ray microscopy experiment is we take a finely focused X-ray beam, and we can, with spectral resolution of 25 nanometers or even better, start to resolve differently lithiated domains within individual particles and across ensembles of particles. And this then allows us to probe very finely the phase evolution as a function of lithiation and as a function of particle geometry in these structures. Okay, so here's an example. Depending on the orientation of the beam of the particle with respect to a beam, our X-ray focused X-ray beam, we can, we typically will see a core shell behavior where we've got an unlithiated core or and a more surface lithiated shell. This is again some characteristic data that points to the formation of small polarons in V2O5 and the really the primary diffusion limitations that arise from small polarons. And I also want to sort of take a second to say that small polarons are quite ubiquitous in most of these oxide systems with large band gaps. This is generally how electron density accumulation will result in small photon being stabilized. Okay, so one of the consequences. Okay, so what are the consequences of small polaron formation, and then these different phase these diffusion limitations? Is one of the consequences is that different particles in an ensemble here, for example, particles 1, 2, 3, 4, are lithiated to different extents. Okay, and so this turns out to be quite. We've spent a lot of time looking at this, and I've talked about this at previous TMS meetings. This turns out to be quite an important thing because many continuum models of batteries systems essentially talk about average forms of lithiation, whereas this really talks. These images illustrate the great spatiotemporal heterogeneity that exists in these systems as lithiation occurs, and as a result of these diffusion limitations arising from small polaron formation and the resulting phase heterogeneities in these systems. Okay, so and you can see here, this is a set of nanowires that have been actually lithiated and delithiated across several cycles. So the small nanowire is completely delithiated, but the bent part of this wire here in 4 has regions of lithium still present, so really corresponding to irreversibly lithiated regions, right? And so that's capacity that has effectively been lost. And so we can dive down a little bit deeper. This is work of David Santos using a bunch of statistical methods and identify these lithium-rich striations that actually form in these delithiated wires. So it's really, really cool. Especially during lithiation, the domain that we see, and I sort of showed you an example of this here, tend to be somewhat random, not entirely random. They're determined, the specific morphology, they're determined by these nucleation restrictions along the wire, which could be affected by local topology or the presence of local defects. Whereas during delithiation, we actually start to see something that looks like what you would expect from thermodynamics from spinodal decomposition. So we can start to see these lithium-rich striations, and the majority phase corresponds to low lithiated alpha, whereas then you've got these striations of this epsilon lithium V2O5 phase. And working with Baishang Xu's group and Yang Bai at TU Darmstadt, we can essentially model this quite nicely as the interplay between the energetic gain from phase separation, the presence of double well potential, and the penalty resulting from the formation of a phase boundary. So the specific striations that are formed reflect the energy required to form a phase boundary, multiplied by, of course, the dimension of the wire. This is why you see it in these confined particles where these striations become possible. So beyond the cool idea of seeing phase separation and so vividly, as you can see in these images, the computational phase separation, there's other implications. So of course, at each of these phase boundaries, you have some lattice mismatch, and this lattice incommensurability gives rise to these stresses. And we're just plotting one mesostresses here because the orientations aren't entirely clear. But in principle, of course, we can plot directional stresses and analyze those as well, and we have in some more recent systems, and this then results the buildup of stress changes the diffusion directionality and diffusion rate in these structures. The buildup of stress is which in turn then changes further the specific heterogeneities that are formed in these systems. So there's this complex interplay between mechanics and thermodynamics and the electrochemistry that has to be taken into account, and some of these models that Baishang's group are developing are allowing us to do just that. And this is another example. Again, very common motif that is seen are these interconnected particles, right? This is primary particles that are interconnected. And again, you can see here, blue represents the most lithiated, red is the least lithiated. The tips of the wires tend to be blue, but then you see these large scale heterogeneities, especially also heterogeneities at the interfaces where they connect. And this is again a beautiful paper coming out from Baishang Xu's group, which will look at some of the across grain boundary transport and how that results in local depletion at grain boundaries. And so essentially, the takeaway message is that these atomistic diffusion limitations resulting from small polarons, resulting from these electronic structure peculiarities, have some real consequences in single particles, in ensembles of particles, and then at electrodes. And you can sort of see that here, where you get this stress generation in bulk B2O5 as a function of lithiation, delithiation. And you can see this here for a pre-strained particle. The stress accumulation as a result of the phase coexistence, phase heterogeneities, ultimately results in fracture, right? And this is a pretty extreme case where something was already sort of primed to fracture. But we've seen other examples of cohesive delamination of surfaces, where the surface being more lithiated starts to peel off, and paving the way. We think this is even really the pathway to amorphization of surfaces is just the stark difference between lithiation, surface lithiation, and bulk diffusion. One way to mitigate this is shown here in blue. This is still the potential curve, but one way to one hint towards this is, of course, you can move away from bulk B2O5 to small particles where you don't have as much stress accumulation, but that, of course, then gives rise to another host of problems related to your volumetric densities that are possible or accessible. Okay, so I've spent a lot of time admiring the problem. How do we go from here? Where do we go from here? What can we do to mitigate these challenges? So I'm going to try to spend the rest of my time talking about really two distinctive approaches. Well, first is looking at mesoscale engineering of the electrode architecture to address these challenges. And the second is going back to the drawing board and really doing atomistic design to overcome these consequences of polaron localization, right? So on the one hand, okay, so we've learned that phase heterogeneities, phase separation gives rise to accumulated stresses that then even at the macroscopic level will accumulate and in all sorts of places and give rise to failure. And you can see this here at a bend in a pre-bent wire. We see hot spots that are being formed by scanning transmission X-ray microscopy, and then you can get sort of stress homogeneities. So I'm going to talk first about this left side, and then I'm going to come back here and spend a little bit of time thinking about really a chemical approach to electrode design. Okay, so one way we've gone about this is harnessing curvature. Okay, so we saw how curvature, both in this particle, this is a irreversibly deformed bent wire, as well as prior examples here where we've got structures that have been elastically bent. Okay, so curvature can clearly affect diffusion pathways. So what if we have continuous curvature in these systems? So we made these inverse opal structures where we form, polystyrene sphere monolayer. We infiltrate with the precursor, and then we remove it, and we can get these structures. And you can see here really beautiful sort of cup-like structures that we can form, very homogeneous and HCP lattice overall. By Brahman spectroscopy, they're crystallized as orthorhombic B2O5, and with the preferred orientation. And and we can grow these structures across fairly large scales, even millimeters. Okay, and one of the things that we see when we take some images, unlike all of these hotspots that you saw in individually curved nanowires, or even in the core shell behavior we saw in individual particles, we see this completely homogeneous lithiation, okay, across these inverse opal clusters. Okay, so no matter where you look across these millimeter-sized domains, you see very homogeneous signatures in the vanadium L3 and oxygen KH spectra. And with that, the only differences, of course, are due to overall density, but the line shapes are the same. So essentially what we've been able to do is, by using curvature, we can improve the rate performance, because we've got a very large area of electrolyte contact and the diffusion path lengths are decreased. And we are also getting homogeneous lithiation take place across the entire structure, but without generating this elastic misfit strain that we observe across all of these single particles, these single wires, right? So either elastic misfit strain results from core shell morphologies for straight nanowires, or because there's hot spots and cold spots that form across these wires. So having this curved cup-like architecture gives us really beautiful, homogeneous lithiation at high rates. A very high rates of lithiation are also possible. So we've essentially used electronic structure mapping to correlate these orbital considerations to battery failure mechanisms, and then identify the way to mitigate it and to improve the lifetimes of batteries. And here's some images that show you also the concentration maps that we've been able to extract from StickSim in conjunction with modeling, and then also that translated to really fairly homogeneous strain stresses across the system. Okay, and yeah, not surprisingly, higher capacity as well as much better cycle life retention for these inverse opal electrodes, accelerated kinetics, and perform much better with respect to capacity at retention at lower C rates. So here's a way to start addressing some of these impediments to diffusion that arise from polaron formation and phase coexistence through geometrically texturing electrodes. Okay, and so yeah, so the takeaway message is that curvature is good. This is a cartoon that Steve Cranford posted for us on Twitter, and these curves are quite cool if you're trying to mitigate diffusion impediments. And these nanoball architectures allow us to really start getting the best of both worlds, both high rate performance as well as mitigating the elastic misfit strain that can be quite ruinous to batteries. Okay, so changing gears a little bit. Another way to do this is through chemical modification. Okay, so you can modify structures to reduce the elastic misfit strain by changing the degree of lattice incommensurability. So really the idea here is that we've got two phases, right? Two differently lithiated domains. And by incorporating dopants, could you bring them closer to each other? So that's one idea we've been pursuing. And a second one is, could you altogether go towards the entirely different V2O5 frameworks that don't have some of these design flaws that this orthorhombic phase of V2O5 had? And so, of course, the big major design flaw is the square pyramidal nature and its split off conduction band that gives rise to these polarons. So we've spent a lot of time identifying and stabilizing metastable V2O5 phases. We've conceptualized and have in some form or the other more than 10 new metastable structures that allow us to essentially define entirely different diffusion pathways for ions based on rejigging the atomic connectivity in these structures. Okay, so the idea here is that composition is not structural destiny, that you can think about these as being energy landscapes, and where the thermodynamically stable phase could be the deepest well, there exist local minima that are quite readily accessible. And actually, V2O5 turns out to have a very rugged landscape. And these metastable phases, when you stabilize them, oftentimes have very intriguing diffusion path phase that allow us not just to do lithium ion insertion, but also magnesium and calcium ion insertion. Okay, and so I'm going to, in the interest of time, this is alpha V2O5. I'm going to show you just a few examples of structures that we have that are well characterized. This is one we particularly love, zeta V2O5. Okay, it's got these 1D tunnels that are defined, and these 1D tunnels tend to be really great for inserting lithium ions as well as magnesium ions. Here's another gamma structure that has been known, and we make this by, we actually take alpha V2O5, lithiate it all the way to gamma, and then we take the lithium ions out chemically, and we can stabilize this distorted puckered structure. And then here's another one that we made that is a layered structure of lambda V2O5. Okay, and again, why does this work so well? So I remember the beginning of my presentation, I talked about the 8 to 3 to 8 change in coordination number. Well, so in gamma prime V2O5, the change in coordination number is much smaller, 5, 3, 4, 3, 5, or in zeta 4, 3, 5, 3, 4, or in lambda 6, 4, 6, 4, 6, right? So much less extreme changes in local coordination environment as ions move through the lattice. And that's one takeaway. And the second takeaway, for example, in zeta, most of these coordination environments are not favored for ions like magnesium. So magnesium is essentially trapped in this frustrated coordination geometry at all times, which then allows us to move magnesium ions through. This is still one of the best in class compounds for magnesium ion. There's essentially greater band curvature in these compounds due to decreased effective polaron mass, because instead of having this dxy sticking out like a sore thumb, we've got these states being strongly overlapped, and so essentially changing the structure and bonding and having these more degenerate 3D states can greatly modify polaron delocalization. And you can see here, these are some calculations on how much the polaron barrier is diminished in these compounds. So practically, we can now, this is a metastable compound, and people often think that metastable compounds are produced in trace quantities or something like that. So just to dispel that notion, we can grow single crystals of this. We can grow kilograms of this. We've got two methods. We can start with either a copper precursor, a copper V2O5 or a silver V2O5, and extract copper or silver, and we can generate this beautiful tunnel structure almost entirely emptied of the native cations. And so, yeah, in a sense, you can think about this as playing chemical Jenga. And we demonstrated that we can insert magnesium through reaction with n-butyl magnesium. And we can take magnesium out by reaction with NOBF4. And we've solved structures of the magnesiated phase. And here's some cycling data on magnesiation. And working with Jordi Cabana's group, we've also made nanoparticles of this that actually do a little bit better for capacity at higher temperatures. Now, I promise you, talking about single crystals, this is one of the reasons this works so well is that the change in lattice constants is almost negligible as ions come into the structure. And so we can actually lithiate entire single crystals and they don't actually end up falling apart. So we can get single crystal diffraction patterns as a function of different lithiation extents. This is Joseph Handy's work that we're very happy to publish in Angewandte last year. And we can essentially map for the first time, map atomic diffusion pathways. We can actually look at these isosurfaces, electron density surfaces along the tunnel structures and come up with experimental pathways. So we can figure out which sites are occupied first, identify sites occupied at high occupancies of lithium ions, and then actually map the connectivity between these sites to figure out where exactly the diffusion occurs. And by understanding this, of course, this is a very powerful means of changing, modifying structure, knowing, being informed by the atomistic diffusion pathways. Okay, and another cool thing that Joseph has been doing, I'm going to talk about, is the idea of protecting groups in intercalation chemistry. So because we can work with single crystals, if you've got a little bit of copper in there, if you've got a little bit of silver in there, where does the lithium then go? So if you end up blocking some of the sites in the tunnel, could you direct the lithium ions down specific routes? And this has been very exciting because we can specifically position lithium ions in about 4 sites, depending on what else is present. Here's another structure. Again, we can grow single crystals of this. This is not a one-off fluke. We're again pretty excited about this whole family of compounds. Epsilon copper V2O5. We can take copper out and stabilize lambda V2O5, and it's a fully van der Waals compound. It can be cleaved by Scotch tape. We have a collaboration with Shing Tu's group at Texas A&M working on these structures. And so overall, I think you could think about this as this Kirigami approach to materials design. We make MX-V2O5 phases with different metal cations, and depending on the choice of the metal cation precursor, we crystallize different V2O5 frameworks, and then we can remove those metal ions. And if we do it correctly, the V2O5 framework is frozen in the structure that was native to those cations, but now we can use those as sort of these frustrated coordination environments for all sorts of other cations like lithium and magnesium and calcium. Okay, and so accessing metastable phase space through topochemistry allows us to access this huge space. And I'm just going to go through a couple of slides showing you some crystallographic relationships. Not going to go too much into detail, but you can see how, for example, through inserting an ammonium ion and removing it, we can stabilize this beta structure. And through copper or silver, we can stabilize this zeta structure. And through other ions like strontium, we can stabilize layered structure that we can then exfoliate, or we can remove the metal ion, stabilize fully layered structure, and exfoliate them as required. So this is really a massive playground. That's really all I'm looking to show, and essentially just playing chemical Jenga, and the fact that composition is not structural destiny. We can pack these holes with other ions and get entirely new kinds of compounds. Okay, so I'm just going to leave some final thoughts. Okay, cathode design, hopefully this has come through at the beginning of the talk. It requires consideration of atomistic and electronic structure, as well as phase evolution along length scales. Metastable phase space provides opportunities for a much expanded palette. Single crystal electrochemistry enables an atomistic view of diffusion phase. And again, we're very excited about this because this is there's a real opportunity here, not just to be guessing at this, to be performing simulations, but to be really seeing in real space what exact pathways are traversed by the ions. And that linking length scales is really imperative in both experiment and theory for us to solve the whole problem, not just a part of the problem, because all of these sort of fundamental physical science phenomena, electron correlation phenomena, have these very substantial implications at longer dimensions. So I'm going to stop here, and thank you so much for listening, and I'd be happy to take any questions you might have. Thank you.